We're going to be going over implementations for stacks and queues, mainly the static implementation of both of these, and then a circular implementation for the queues. So let's start with the stack. We can have an inner array for a stack, and let's say it's going to have 10 spots just as a default, and each one of those spots is going to be defined by an index. If we have a variable, say in this case called top, you can call it anything that you'd like, it's sort of going to give us the index where the top of the stack holds the necessary element. So every time that we add something, we're going to want to add it to the top, and every time that we want to pop something, then we want to pop it from the top, just like a stack would work. Now, our somewhat pseudocode for this would be for push. You want to check if you're full. If you are full, then you return the appropriate exception. Otherwise, you want to insert the element at the top of the inner array, and then you want to increase the top by 1. If we're looking at pop, we're going to do something similar. We're going to check for empty. We're going to decrease the top, and then we're going to return whatever is in that spot for the inner array. So let's look at how this would work. Let's say that we wanted to push the number 99 into the stack. The number 99 would go into the top, and then we would increase top by 1, and we would be in the next spot. This would be the top of the stack. If we wanted to, say, push again another number, we would push it at this spot, and then we would increase after adding it or inserting the element at that spot. And we would continue doing this for any amount of pushes that we'd have. So we'd end up with pushing these elements onto the stack, and then our top would be in that index. Let's say that we wanted to pop though. So in this case, we want to decrease the index or the marker by 1. Top minus 1 would be at index 5 in this case, and then we would return whatever is in that spot. We would end up with the number 33 if we popped, and then our top would be in that spot. Now there's a small problem with this. After we've decreased the top, well, we haven't really done anything to this element. This element stays the same. So we're going to have to null this element. Otherwise, we're still going to have 33 in that spot. In this case, we can update our algorithm by making sure that we null that spot, and then we return the appropriate element. Now let's look at the implementation for a static queue. So we just saw a static stack. By moving top up and down, we're able to get whatever we need at the top of the stack. And you might say, why can't we just do that for the queue then? We have an inner array, we have the top, and then we can go ahead and queue stuff up. So if we wanted to queue things, we could use the top, and we would end up queuing things at the top one by one until we end up at index 6. And that seems to work. So push could use just one variable. But then if we wanted to dequeue, remember that a queue will give you back the first thing that we put in. So the first thing that came into this queue was the number 99. And if we look back at it, the first thing that was in queued was 99. So ideally, whenever we dequeue, we want to dequeue 99. But in this case, we don't have that index, and we don't have a reference to where that spot is. And we could say, well, let's just do 0. Well, yeah, you could do 0, but then the next time you want to dequeue, 77 should get dequeued. And how are you going to know that you should be a 1, or you should be a 0, or you should be a 2? So instead, we're going to use 2 variables. One's going to be called front, and the other one's going to be called back. Now, by having 2 variables, we're able to use back to enqueue, so we know exactly where the new element's going to be enqueued at. And then whenever we want to dequeued, we use front. So we're going to dequeue whatever's at the front. In this case, if we dequeue, we're going to get whatever is at index front, and we are going to move the front to the next spot, and we're going to null the element that we just dequeued. And that works perfectly well. So if we dequeue again, we're going to remove the element at the spot front, and then we're going to null that element, and we're going to continue moving that forward. Now you can come up with your own algorithm for this. I'm not going to give you pseudocode for it, but this is generally how this would work. As we continue to do this, maybe we want to enqueue something. So if we want to enqueue, then we just use back. Go ahead and enqueue at the back and then move back forward. And this seems like it's working just right. Let's say that we want to enqueue 3 more things: 555, 322, and 888. We do this, and also perfectly fine. But if we wanted to enqueue one more time, say we wanted to enqueue the number 1, this would say that it's full. Like, we have no way of saying use up the other spots that we already got rid of. So we need some way to make sure that we wrap around. And in this case, it would be the reference to the circular queue. We want to circle back around to the spot that's available if, in fact, it is available. In this particular case, it is available. We have 2 spots, 0 and 1, or index 0 and index 1. So what we should be doing is, in our enqueue algorithm, we want to wrap back around, and now the back is going to be at index 0, creating this sensation of a circle. So we have sort of a moving target of where the front and the back is. So now the front, if you think of it as a circular array, the front is at index 2, and then the back is at index 1, or like the last element possible would be at index 1. If we wanted to enqueue 1, in this case we would enqueue 1, and then we would want to move back 1 over to index 1, and we would continue to do this until we're actually full. And at some point,